Before drifting into tonight's journey through one of the most mysterious ideas in modern physics, take a moment to like this video and subscribe to Cosmic Bedtime Stories. Every like and subscription helps bring more deep space documentaries designed for relaxation, learning and sleep. Now imagine a possibility that sounds impossible at first. What if the entire universe, every galaxy, every star, every planet and even every moment of time exists inside a black hole? For decades, some physicists have explored clues that hint at a surprising connection between the structure of our universe and the strange physics hidden beyond a black hole's event horizon. Tonight, this documentary explores 7 levels of black holes, from the familiar objects formed by dying stars to the extreme theories that suggest our cosmos itself could be the interior of something far larger. Along the way, it reveals what science knows, what remains uncertain, and why black holes continue to challenge humanity's understanding of reality itself. Settle in, relax, and prepare for a journey into the deepest mysteries of space. The observable universe stretches outward in every direction, as the largest region that science can directly examine. It contains every galaxy whose light has had enough time to reach Earth since the beginning of cosmic expansion. Beyond that visible limit, space may continue much farther, perhaps without end, but observations cannot yet determine its full extent. What can be studied is the enormous sphere of visibility surrounding humanity, built from light that travels across immense distances and carries information from remote corners of the cosmos. From Earth, the night sky appears as a dark dome scattered with stars. Careful observation reveals that many faint patches of light are not stars at all. They are entire galaxies, each containing vast numbers of stars, clouds of gas, clouds of dust planets, and black holes. Modern telescopes show that these galaxies fill space in extraordinary abundance. The observable universe contains hundreds of billions of galaxies, and ongoing studies continue to refine estimates as instruments become more capable. The scale involved is difficult to visualize through ordinary experience. Distances inside cities, countries, and even across Earth become insignificant when compared with cosmic dimensions. Light itself, the fastest known traveller in nature, requires years to cross the gaps between neighbouring stars. Between galaxies, the distances become far larger still. The observable universe spans tens of billions of light-years in every direction from Earth, creating a realm so extensive that ordinary intuition offers little guidance. Despite this vastness, astronomers discover that the observable universe follows patterns. Galaxies are not distributed completely at random. They gather into groups and clusters. Clusters join larger associations. Across enormous distances, matter forms a network of filaments and concentrations separated by immense regions containing relatively little matter. This arrangement creates a structure sometimes compared to a web, although the comparison serves only as a simple image rather than a precise description. Within this observable realm, the same physical laws appear to operate everywhere that observations can reach. Light behaves according to the same principles. Gravity influences matter in similar ways. Atoms produce recognizable signatures in distant galaxies, just as they do in laboratories on Earth. This consistency allows astronomers to study regions that cannot be visited. The light arriving from remote locations serves as a messenger, carrying information about temperature, motion, composition, and age. Looking farther into space also means looking farther into the past. Light requires time to travel. A nearby star may appear as it existed a few years ago. A distant galaxy may appear as it existed millions or billions of years ago. Some of the most remote objects ever observed reveal conditions from an era when the universe was much younger than it is today. Telescopes therefore function not only as instruments for seeing distant places, but also as instruments for studying ancient periods of cosmic history. The observable universe contains many kinds of objects. Stars convert hydrogen into helium within their interiors, producing energy that shines across space. Planets orbit stars. Nebulae, which are large clouds of gas and dust, provide material for future generations of stars. Galaxies collide and merge over long spans of time. Invisible dark matter contributes most of the matter associated with galaxies and clusters, according to current evidence, although its exact nature remains unknown. Dark energy appears to influence cosmic expansion on the larger scales, yet its underlying cause also remains uncertain. Against this enormous background, black holes occupy only a small fraction of space. They are not the dominant visible feature of the cosmos. Most regions contain vast emptiness between stars and galaxies. Nevertheless, black holes attract scientific attention because they represent some of the most extreme environments known. Their gravity can become so intense that familiar ideas about space and time require careful examination. Even so, when viewed from the widest possible perspective, black holes exist as components within the larger cosmic landscape, rather than as isolated mysteries disconnected from everything else. The observable universe presents a remarkable balance between complexity and order. Individual galaxies differ greatly from one another. Some actively form stars. Others contain older stellar populations. Some appear as elegant spirals, while others possess more rounded forms. Yet broad patterns emerge when enough galaxies are studied together. The same basic ingredients appear repeatedly across cosmic distances. Matter gathers under gravity. Stars form, evolve, and eventually die. Galaxies grow and interact. The observable universe displays variety without abandoning coherence. Astronomers rely on many forms of observation to investigate this immense realm. Visible light reveals only part of the picture. Radio waves expose cold gas. Infrared observations penetrate dust and reveal hidden structures. Ultraviolet light traces energetic processes. X-rays and gamma rays reveal some of the most extreme events in nature. Together, these different forms of light provide a more complete understanding of the cosmic environment. Measurements collected over many decades indicate that the observable universe has evolved over time. Galaxies observed at great distances often appear different from nearby galaxies because they are seen during earlier stages of cosmic history. This gradual change provides important clues about how the present cosmic structure emerged. Observations indicate that the universe was once denser and hotter than it is today. The evidence supporting this conclusion comes from many independent lines of investigation. Standing within this observable realm, humanity occupies no central location. Every observer elsewhere would see a similar sphere of visibility centered on their own position. The observable universe is therefore not a physical edge marking the end of existence. It is a limit imposed by the finite age of cosmic expansion and the finite speed of light. Beyond the horizon of observation, additional regions may exist, but current science cannot directly examine them. The largest accessible view of reality therefore begins not with black holes, but with the immense stage upon which all known cosmic phenomena appear. Galaxies, stars, planets, dark matter, and black holes all exist within this observable domain. It forms the broadest region that evidence can presently illuminate, providing the outermost layer of exploration before attention turns toward specific structures embedded within the cosmic landscape. The observable universe does not remain static. On the larger scales accessible to observation, space changes over time. Galaxies are not simply scattered through a fixed cosmic stage. Instead, the stage itself expands. This expansion represents one of the most important discoveries in modern astronomy and forms a fundamental part of the current understanding of the universe. The evidence emerges gradually through careful observation. During the early 20th century, astronomers begin measuring the light arriving from distant galaxies with increasing precision. Light can be separated into its component colors, producing patterns that reveal information about the source. The same atomic elements create recognizable signatures whether they are examined in laboratories on Earth or observed in remote galaxies. These signatures provide a powerful tool for measuring motion. When astronomers examine distant galaxies, they discover that the light arriving from many of them appears shifted toward longer wavelengths. This phenomenon is known as redshift. The effect resembles the change in pitch heard when a moving source of sound travels away from an observer. In the case of light, the shift indicates that distant galaxies are generally moving away. At first, this result appears surprising. The expectation for many centuries is that the universe might remain essentially unchanged on the larger scales. Yet repeated observations reveal a clear pattern. The farther away a galaxy lies, the greater its average redshift tends to be. Distance and recession become linked through a consistent relationship. The most distant observable galaxies generally appear to recede more rapidly than nearby galaxies. This observation leads to a profound conclusion. The galaxies are not necessarily rushing outward from a central location through empty space. Instead, the space between galaxies expands. An observer inside one galaxy sees other distant galaxies moving away. An observer in another distant galaxy would see a similar pattern. The expansion occurs throughout the large-scale fabric of the observable universe. To understand this idea, astronomers often use simplified images, though none perfectly represent reality. The important point is that cosmic expansion does not resemble an explosion moving outward into surrounding emptiness. Observations indicate that space itself changes over time. Distances between large cosmic structures increase as expansion proceeds. The consequences become visible across immense spans of time. Galaxies separated by vast distances today were closer together in the distant past. If the observed expansion is traced backward mathematically, the universe appears increasingly dense and hot. This conclusion forms one of the foundations of modern cosmology, the scientific study of the universe as a whole. Evidence for expansion comes from multiple sources rather than a single observation. Measurements of galaxy redshifts provide one line of evidence. Another comes from the cosmic microwave background, a faint glow of radiation that fills space in every direction. This radiation represents a relic from an early period when the universe is much hotter and denser than it is today. Its properties match predictions derived from expanding universe models with remarkable precision. Additional evidence comes from the distribution of galaxies themselves. The large-scale arrangement of matter throughout space contains patterns that reflect conditions in the early universe. Modern surveys mapping millions of galaxies reveal structures consistent with long-term cosmic expansion. Independent measurements repeatedly converge on the same broad picture. The rate of expansion is not constant across all eras of cosmic history. Observations indicate that gravity influences the expansion process. Gravity acts as an attractive force between concentrations of matter and energy. For many years, astronomers expect that gravity might gradually slow the expansion. However, increasingly precise observations reveal a more complicated reality. Studies of distant stellar explosions known as supernovae suggest that expansion presently accelerates rather than slows. Galaxies continue moving apart, and the rate of separation appears to increase over vast distances. To describe this behavior, cosmologists introduce the concept of dark energy. The term refers to whatever process drives this acceleration. Observations strongly support the existence of the effect itself, but the underlying physical cause remains uncertain. This uncertainty occupies an important place in modern science. Observations indicate that cosmic acceleration occurs. Measurements from different methods broadly agree, yet the fundamental nature of dark energy remains one of the largest unresolved questions in cosmology. Scientists continue investigating possible explanations while carefully comparing theoretical predictions with observational evidence. Within this expanding universe, black holes exist as local gravitational structures. They influence nearby stars, gas, and light. However, the expansion of space operates on scales vastly larger than individual black holes. A galaxy containing a black hole still participates in cosmic expansion as part of the broader universe. The two phenomena belong to different levels of cosmic structure. Expansion also affects the observable horizon. Because light travels at a finite speed, and the universe evolves over time, the observable region changes. Some distant light reaches Earth only after journeys lasting billions of years. The observable universe therefore represents both a spatial and temporal concept, combining distance with the history of cosmic expansion. As observations improve, astronomers continue refining measurements of the expansion rate. Different methods occasionally produce slightly different results, creating an active area of research. These differences are carefully studied because they may reveal new aspects of cosmic physics or previously unrecognized sources of uncertainty. At present, observations clearly support expansion itself, while some details regarding its exact rate remain under investigation. The expanding universe transforms the way humanity understands cosmic history. Space is no longer viewed as an unchanging backdrop. Instead, it becomes dynamic. Distances evolve, structures grow, galaxies move farther apart over immense intervals. The observable cosmos becomes a living system with a measurable past and an unfolding future. From the broadest perspective currently accessible, every galaxy, star, planet, cloud of gas and black hole exists within this expanding framework. The universe reveals itself not as a static arrangement frozen in time, but as an evolving cosmic environment whose largest scales continue to change. The expansion of space provides the setting within which all later structures emerge and develop, shaping the grand landscape that astronomy observes across the depths of cosmic time. The expanding universe contains matter distributed across distances so vast that even light requires millions and billions of years to travel between many regions. Yet this matter does not form a smooth, uniform fog. When astronomers map the positions of galaxies across the observable cosmos, a remarkable pattern emerges. Galaxies gather into immense structures, creating a large-scale architecture that extends across hundreds of millions of light-years. This architecture forms the cosmic web, the broad framework within which galaxies, clusters, and superclusters occupy space. From a great distance, a single galaxy appears as only one small point within a much larger arrangement. Galaxies rarely exist in complete isolation. Gravity gradually draws neighboring galaxies toward one another, forming groups. The Milky Way itself belongs to such a group. Within these collections, galaxies orbit shared centers of gravity over immense spans of time. Their motions are slow on human timescales, but significant across cosmic history. Larger than galaxy groups are galaxy clusters. A cluster may contain hundreds or even thousands of galaxies bound together by gravity. These enormous systems rank among the largest gravitationally connected structures in the universe. Observations reveal galaxies moving through clusters at tremendous speeds. Between the galaxies lies extremely hot gas that emits X-rays. This gas contributes a substantial portion of the ordinary matter within clusters. Studies of galaxy clusters reveal something unexpected. The visible matter alone cannot account for the motions observed. Galaxies move as though much more mass is present than telescopes can directly see. This evidence becomes one of the strongest indications for dark matter. Dark matter does not appear to emit, absorb, or reflect light in ways that current instruments can directly detect. Nevertheless, its gravitational influence becomes visible through the motions of galaxies and the bending of light. Dark matter appears to form the underlying framework upon which visible structures develop. Over billions of years, gravity amplifies tiny differences in matter distribution. Regions containing slightly more matter attract additional matter. Gradually larger concentrations emerge. Galaxies and clusters grow within these gravitational wells. According to current models, dark matter plays a central role in this process. When astronomers expand their surveys to encompass millions of galaxies, they discover that clusters themselves are not randomly scattered. Instead, clusters connect through long filaments composed of galaxies' gas and dark matter. These filaments stretch across immense distances. Between them lie enormous voids where relatively little matter exists. The result resembles a network of interconnected strands surrounding vast regions of emptiness. The term cosmic web serves as useful description for this arrangement. It does not imply actual threads suspended in space. Rather, it refers to the large-scale pattern created by matter under the influence of gravity. Computer simulations based on accepted physical laws produce structures remarkably similar to those observed through telescopes. This agreement strengthens confidence in the current understanding of cosmic evolution. Within these immense structures, individual galaxies often experience complex histories. Some remain relatively undisturbed for long periods, others interact with neighbors. Galaxies may pass close enough to distort one another through gravity. Over time, some merge completely. These mergers contribute to galactic growth and influence the distribution of stars, gas, and dust. The largest recognizable collections of clusters and groups are often called superclusters. These vast regions contain many interconnected structures. However, on the greatest scales, even superclusters participate in the broader cosmic web rather than existing as isolated systems. The web itself becomes the dominant pattern. Observations of the cosmic web require enormous surveys. Astronomers measure the positions and distances of millions of galaxies. Sophisticated instruments gather light from countless sources across the sky. The resulting maps reveal a universe filled with structure extending far beyond anything visible through ordinary observation. Regions that appear empty in small telescopes become components of a much larger cosmic landscape. Light itself helps reveal the invisible portions of this structure. Gravity bends the paths of light rays traveling through space. This effect, known as gravitational lensing, allows astronomers to estimate the distribution of mass, including dark matter. By studying subtle distortions in the appearance of distant galaxies, researchers construct maps of otherwise unseen matter. These observations indicate that dark matter follows patterns closely related to the visible cosmic web. The cosmic web also preserves information about the history of the universe. Its structure reflects conditions present long ago when matter distributions differ only slightly from place to place. Over billions of years, gravity transforms these small variations into the large-scale structures observed today. In this way, the modern universe retains a record of its earlier stages. Despite the immense complexity visible in cosmic surveys, broad simplicity remains. Gravity acts as the primary architect of large-scale structure. Matter gathers where gravity draws it. Regions with greater mass attract additional matter. Over long intervals, this process produces clusters, filaments, and voids. The resulting architecture spans much of the observable universe. Within these vast structures reside countless stars and planets. Entire galactic civilizations, if any, exist elsewhere, would occupy only tiny locations within the immense web. Human history itself unfolds inside a single galaxy, situated within a group embedded within larger cosmic structures. The scale difference is extraordinary. Individual worlds become almost invisible against the backdrop of the larger cosmic arrangement. Black holes exist throughout this architecture. Some reside within ordinary galaxies, others occupy galactic centers, yet from the perspective of the cosmic web they remain localized objects embedded within a much greater framework. The web itself represents the large-scale organization of matter across the observable universe shaped by gravity over billions of years. As astronomy surveys increasingly larger regions of space, the universe reveals itself not as a random scattering of galaxies, but as a connected cosmic landscape. Filaments stretch across unimaginable distances. Clusters gather along these structures. Vast voids separate them. The cosmic web emerges as one of the defining features of the observable universe, providing the broad architectural setting within which all galaxies, stars, planets, and black holes take their places. Within the immense architecture of the cosmic web, galaxies shine as islands of stars separated by vast expanses of space. Inside many of these galaxies reside objects unlike ordinary stars, planets, or clouds of gas. These objects do not emit light through nuclear fusion as stars do. They do not reflect sunlight as planets do. Instead, they reveal their presence primarily through gravity. These are black holes, among the most thoroughly studied and yet most unusual objects known in modern astrophysics. The idea of a body whose gravity becomes so strong that even light cannot escape has deep historical roots. Early thinkers consider whether gravity might become powerful enough to prevent light from leaving a massive object. Such ideas remain speculative for many years because no evidence exists to show that such objects actually occur in nature. The situation changes dramatically during the 20th century as the understanding of gravity advances. A major development comes from the theory of general relativity developed by Albert Einstein. In this theory, gravity is not simply a force acting across space. Instead, mass and energy influence the geometry of space and time themselves. Massive objects alter the structure of space-time, and other objects move along paths shaped by that geometry. General relativity successfully explains many observed phenomena and becomes the foundation for modern studies of black holes. The mathematical solutions of general relativity indicate that under certain conditions matter can become compressed into an extremely compact region. If enough mass occupies a sufficiently small volume, gravity grows so strong that a boundary forms around the object. Beyond this boundary, known as the event horizon escape, becomes impossible according to current understanding. Light emitted inside cannot travel outward to distant observers. Information carried by that light also remains confined. For many years, black holes exist mainly as theoretical possibilities. Astronomers suspect they may form through the deaths of massive stars, but direct evidence remains limited. Gradually, observations begin to reveal objects whose behavior matches black hole predictions remarkably well. Invisible companions in binary star systems appear to possess enormous mass concentrated into very small regions. Gas falling toward these unseen objects becomes extremely hot and emits powerful radiation. The observations strongly suggest the presence of black holes. Today, evidence for black holes comes from many independent methods. Astronomers observe stars orbiting invisible massive objects. They detect intense radiation produced by matter falling inward. They measure the motions of gas near compact gravitational sources. They study gravitational waves, ripples in space-time produced when black holes collide and merge. These diverse observations consistently support the existence of black holes throughout the universe. Black holes themselves cannot be seen directly in the usual sense, because they do not emit light from within the event horizon. However, their influence on surrounding matter often becomes visible. Gas spiraling inward may form an accretion disk, a rotating structure heated to extraordinary temperatures by friction and gravitational effects. Such disks can radiate across many wavelengths, including visible light X-rays and radio waves. The surrounding environment therefore often reveals the presence of the hidden object at the center. One of the most significant achievements in modern astronomy occurs when scientists obtain images of the immediate surroundings of black holes. These images do not show the black holes themselves. Instead, they reveal bright material orbiting nearby and a dark central region associated with the event horizon. The results agree closely with predictions derived from general relativity. They provide powerful confirmation that black holes behave as expected under current physical theories. Black holes appear in several size categories. Some form from massive stars and possess masses several times greater than that of the Sun. Others contain millions or billions of solar masses and occupy the centers of galaxies. Observations indicate that both categories exist widely throughout the observable universe. Additional intermediate cases may also occur, although their populations remain an active area of research. Despite their reputation, black holes do not function as cosmic vacuum cleaners, pulling everything inward indiscriminately. At sufficient distances, their gravity behaves much like that of any other object possessing the same mass. If the Sun were somehow replaced by a black hole of equal mass, Earth would continue orbiting in nearly the same way. The primary difference would be the absence of sunlight and heat, rather than a sudden gravitational catastrophe. The event horizon serves as the defining feature of a black hole. For a distant observer, it marks the boundary beyond which no returning signal can emerge. According to general relativity, this boundary is not a physical surface like the ground of a planet. Rather, it is a region in space-time where escape paths leading outward cease to exist. The event horizon therefore represents a geometric property of space-time rather than a material shell. Black holes also occupy an important place in modern theoretical physics, because they bring together gravity, energy, space, and time under extreme conditions. Questions concerning information quantum processes and the nature of space-time itself often arise in black hole research. While many aspects are understood through established theory and observation, some deeper questions remain unresolved. Scientists continue investigating these issues through both theoretical work and increasingly precise observations. Across the observable universe, black holes appear as natural products of cosmic evolution rather than rare exceptions. They form, grow, interact with surrounding matter, and sometimes merge with one another. Their presence influences stars, gas clouds, and even entire galaxies. Yet they remain only one component within the broader cosmic landscape. Viewed from the scale of galaxies and clusters, black holes are localized concentrations of extreme gravity embedded within a much larger universe. They can be detected, measured, and studied through their effects on nearby matter and light. Observations leave little doubt that black holes exist in nature. They stand as real astronomical objects whose behavior largely follows the predictions of modern gravitational theory, occupying a distinctive place among the many structures that populate the cosmos. Among the various kinds of black holes known to astronomy, the most familiar are those that originate from the lives and deaths of massive stars. These stellar mass black holes occupy a scale much smaller than the giant black holes found in galactic centers, yet they provide some of the clearest evidence that black holes exist in nature. They appear throughout galaxies and represent a natural outcome of stellar evolution under particular conditions. Every star begins as a cloud of gas. Gravity gradually gathers material together until temperatures and pressures become high enough for nuclear fusion to begin. Fusion converts hydrogen into helium, within the stellar core, releasing energy that produces starlight and counteracts the inward pull of gravity. For much of a star's life, a balance exists between outward pressure generated by fusion and inward gravitational attraction. The future of a star depends largely on its mass. Stars with relatively modest masses eventually shed their outer layers and leave behind dense remnants known as white dwarfs. More massive stars experience different endings. Their greater mass allows them to continue producing heavier elements in their interiors through successive stages of fusion. Over time, their cores become increasingly complex, containing layers of different elements created during the star's evolution. This process cannot continue indefinitely. Fusion reactions generate energy only up to certain limits. When the core accumulates large amounts of iron and similar elements, further fusion no longer provides enough energy to support the star against gravity. The delicate balance that has existed for millions of years begins to fail. Once support from fusion declines, gravity takes control. The core collapses inward with extraordinary speed. Temperatures rise dramatically. Matter becomes compressed to extreme densities. The outer portions of the star may be expelled in a powerful explosion known as a supernova. Such events enrich galaxies with heavy elements that later become parts of new stars' planets and other structures. What remains after the explosion depends again on mass. In some cases, the collapsed core becomes a neutron star, an object of extraordinary density composed largely of neutrons. In other cases, the remaining core contains enough mass that no known force can permanently halt the collapse. Gravity continues compressing the material. An event horizon forms and a stellar mass black hole emerges. Observations indicate that stellar mass black holes commonly possess masses ranging from several times the mass of the Sun to several tens of solar masses. More massive examples have also been identified through gravitational wave observations. The exact mass depends on the original star and on details of its evolution before collapse. Once formed, a stellar mass black hole may remain difficult to detect. A solitary black hole moving through space emits little or no observable light. Its presence becomes apparent primarily through gravity. If it drifts through a relatively empty region of a galaxy, astronomers may have few opportunities to observe it directly. Detection becomes much easier when a black hole exists within a binary system. Many stars occur in pairs. If one member of such a pair becomes the black hole, while the other remains an ordinary star, the gravitational interaction can reveal the hidden object. Astronomers may observe the visible star orbiting an unseen companion whose mass exceeds the limits expected for neutron stars. Such systems provide strong evidence for black holes. In some binary systems, gas from the visible star gradually flows toward the black hole. This material rarely falls straight inward. Instead, it often forms a rotating accretion disk. Friction and compression within the disk heat the gas to very high temperatures. As a result, the disk emits intense radiation, particularly X-rays. Many of the first convincing stellar mass black hole candidates are discovered through these powerful emissions. Modern observations reveal that stellar mass black holes are not merely theoretical curiosities. They appear to be widespread throughout galaxies. The Milky Way alone likely contains millions of them. Most remain undetected because they are not actively consuming material. Their existence is inferred from models of stellar evolution and from the population of black holes that astronomers have already identified. The study of stellar mass black holes advances significantly with the development of gravitational wave astronomy. When two black holes orbit one another closely, they gradually lose energy through gravitational waves. Their orbit shrinks until the objects eventually merge. The collision produces a burst of gravitational radiation that travels across space. Detectors on Earth can measure these signals. The first direct detection of gravitational waves provides dramatic confirmation of black hole mergers. The measured signals closely match predictions derived from general relativity. Since then, numerous additional detections have revealed many black hole pairs. These observations allow scientists to study black holes in entirely new ways, independent of traditional light-based astronomy. Stellar mass black holes also influence their local environments. Their gravity can affect nearby stars, shape the behavior of surrounding gas, and contribute to the evolution of binary systems. However, their influence generally remains limited to relatively small regions compared with the scale of entire galaxies. They're important local actors rather than dominant galactic architects. Although these black holes possess intense gravity near their event horizons, they remain physically small. A stellar mass black hole containing several times the Sun's mass may occupy a region only tens of kilometers across. This combination of substantial mass and compact size creates the extreme gravitational conditions that characterize black holes. Within the broader universe, stellar mass black holes represent one level in a hierarchy of black hole types. They arise naturally from stellar death and can be observed through their gravitational effects, radiation from surrounding matter, and gravitational wave signals. Their existence demonstrates that nature can indeed create regions where gravity becomes powerful enough to form event horizons. As products of ordinary stellar evolution, they provide a direct and observable link between the familiar lives of stars and the more extreme phenomena found throughout the cosmos. While stellar mass black holes originate from the deaths of individual stars, another category of black hole occupies a vastly larger scale. These objects reside in the centers of galaxies and possess masses that can reach millions or even billions of times the mass of the Sun. They are known as supermassive black holes. Among all known black holes, they rank as some of the most influential structures in the observable universe. The existence of supermassive black holes becomes apparent through observations of galactic centers. Many galaxies contain dense concentrations of stars near their cores. As telescopes improve, astronomers begin measuring the motions of these stars with increasing precision. In numerous cases, the observed motions indicate the presence of an enormous amount of mass concentrated within a remarkably small volume. One of the clearest examples lies at the center of the Milky Way. Careful observations spanning many years track individual stars moving around an invisible object. Some stars follow highly elongated orbits, passing extremely close to the central mass before moving away again. The measured motions reveal that several million solar masses occupy a region far too small to be explained by ordinary clusters of stars. The observations strongly support the presence of a supermassive black hole. Similar evidence appears throughout the observable universe. Large galaxies frequently contain central black holes whose masses range from millions to billions of solar masses. The consistency of these findings suggests that supermassive black holes are a common feature of galactic evolution rather than unusual exceptions. The origin of these giant black holes remains an active area of scientific investigation. Observations clearly establish their existence, but the precise sequence through which they form and grow is not fully settled. Several possibilities are studied. Some models propose that they begin as smaller black holes formed from massive stars and gradually accumulate matter over long periods. Other models suggest that very large gas clouds in the early universe may collapse directly into massive seeds that later grow further. Current evidence indicates that multiple processes may contribute. Regardless of their initial origins, supermassive black holes can increase in mass through accretion. Gas dust and occasionally entire stars may move toward the galactic center. Material falling inward carries energy and angular momentum. Instead of plunging directly into the black hole, much of it forms a rotating accretion disk. Within the disk, friction and turbulence convert gravitational energy into heat. The resulting temperatures can become extraordinary. In some galaxies, the central regions radiate enormous amounts of energy across many wavelengths. Such active galactic nuclei may outshine the combined starlight of the surrounding galaxy. When observed from great distances, some of the brightest examples are known as quasars. These objects appear especially common during earlier periods of cosmic history, when galaxies contain abundant gas available for accretion. The brightness of quasars provides indirect evidence for the existence of supermassive black holes. The observed energy output is difficult to explain through ordinary stellar processes alone. Accretion onto a giant black hole offers a mechanism capable of producing the required luminosity. Modern observations strongly support this interpretation. Supermassive black holes do more than simply consume material. Their activity can influence entire galaxies. Energy released by accretion may heat surrounding gas or drive powerful outflows. These processes affect star formation and alter the distribution of matter within galactic environments. As a result, the evolution of a galaxy and the growth of its central black hole often appear interconnected. Observational studies reveal intriguing relationships between galaxies and their central black holes. For example, the mass of a supermassive black hole frequently correlates with properties of the surrounding galactic bulge, the dense central region containing many stars. Such relationships suggest a long history of interaction between black hole growth and galactic development. Despite their enormous masses, supermassive black holes remain tiny compared with the overall dimensions of their host galaxies. A galaxy may span hundreds of thousands of light-years, while the event horizon of its central black hole occupies a much smaller region. Nevertheless, the concentration of mass at the center creates significant gravitational effects within nearby areas. The study of supermassive black holes advances dramatically through high-resolution observations. Astronomers use networks of radio telescopes distributed across Earth to achieve extraordinary detail. These observations produce images of material orbiting near event horizons. The resulting dark central regions and surrounding bright structures agree closely with predictions derived from general relativity. Gravitational waves also contribute to understanding black hole growth. When galaxies merge, their central black holes may eventually approach one another and form binary systems. Over time, gravitational radiation carries energy away, causing the pair to move closer together. The final merger creates a larger black hole. Such events are expected to play an important role in the growth of some supermassive black holes across cosmic history. Although supermassive black holes possess immense gravitational power near their centers, they do not dominate every aspect of galactic behavior. Most stars orbit at distances where ordinary galactic gravity, including contributions from dark matter, plays a greater role. The influence of the central black hole becomes strongest in the innermost regions. Observations indicate that supermassive black holes have existed for much of cosmic history. Some appear in the early universe only a relatively short time after the beginning of cosmic expansion. Their presence presents important clues about the processes that shape large-scale cosmic structure. At the same time, it raises questions about how such enormous masses accumulate so quickly. Within the hierarchy of black holes, supermassive black holes occupy a distinct level. They are larger than stellar remnants by factors of millions or billions. They reside in galactic centers, influence surrounding environments, power some of the brightest known cosmic objects, and participate in the long evolution of galaxies. Their existence demonstrates that black holes are not confined to the scale of individual stars. Nature is capable of creating gravitational structures of far greater magnitude embedded within the hearts of galaxies throughout the observable universe. Before reaching the event horizon itself, there exists a region surrounding a black hole, where gravity increasingly shapes the behavior of matter, light, and time. This outer environment does not consist of empty space. In many cases, it contains gas-dust magnetic fields, radiation and orbiting objects responding to the immense gravitational influence of the black hole. For astronomers, this surrounding region provides most of the information available about black holes, because the black holes themselves remain hidden behind their event horizons. From a great distance, a black hole may appear almost invisible, yet its gravity extends outward indefinitely, becoming weaker, with distance but never completely disappearing. Nearby stars, gas clouds, and other material continue to respond to its presence. The black hole therefore becomes detectable through its influence on surrounding objects long before any material approaches the event horizon. One of the most important features of the environment around many black holes is the accretion disk. When gas moves toward a black hole, it rarely falls directly inward. Most matter possesses some degree of orbital motion. As a result, the material begins circling the black hole while gradually spiraling inward. The gas forms a flattened, rotating structure resembling a disk. Within the disk, neighboring layers of gas move at different speeds. Material closer to the black hole generally orbits faster than material farther away. These differences create friction-like interactions within the gas. Energy is converted into heat. Temperatures rise dramatically. Depending on the size of the black hole and the rate at which material falls inward, parts of the disk may become hotter than many stars. This heating causes the disk to emit large amounts of radiation. Some disks shine primarily in visible light, others produce intense ultraviolet radiation or powerful X-rays. These emissions allow astronomers to study black holes that would otherwise remain extremely difficult to detect. The bright disk effectively announces the presence of the hidden object at its center. The appearance of an accretion disk depends on many factors. The amount of available gas, the black hole's mass, and the orientation of the system all influence what astronomers observe. Some black holes actively consume large quantities of material and become surrounded by brilliant disks. Others encounter little nearby matter and remain comparatively quiet. In such cases, the black hole may be detected only through subtle gravitational effects. Magnetic fields also play important roles in these environments. As electrically charged particles move through the rotating disk, magnetic fields become twisted and strengthened. Under certain conditions, these fields help channel matter into narrow beams that extend outward from the vicinity of the black hole. These structures are known as jets. Jets can travel immense distances through space. In galaxies hosting active supermassive black holes, jets sometimes extend far beyond the visible boundaries of the galaxy itself. The particles within these outflows move at speeds approaching the speed of light. Observations indicate that the energy powering such jets originates from the accretion process, and in some cases from the rotation of the black hole itself. The surrounding region also affects the behavior of light. According to general relativity, gravity alters the paths followed by light rays. Near a black hole, this effect becomes especially noticeable. Light passing close to the black hole may be bent significantly. Some rays travel along curved trajectories before reaching distant observers. This bending contributes to the unusual appearance predicted for the vicinity of a black hole. The effect can create distorted views of surrounding material. Parts of an accretion disk may appear displaced from their actual positions because light follows curved paths through the warped space-time near the black hole. Computer simulations based on general relativity produce striking images of these distortions, many of which correspond closely with modern observations. Another important feature of the surrounding environment is orbital motion. Material can circle a black hole at various distances. Far from the center, stable orbits resemble those around other massive objects. Closer in conditions become increasingly extreme. Gravity strengthens rapidly and the range of stable orbital paths becomes more limited. Astronomers studying the motions of stars near supermassive black holes obtained some of the strongest evidence for the existence of these objects. By tracking stellar orbits over many years, researchers determine the mass concentrated at galactic centers. The observed motions often reveal masses too large and too compact to be explained by any known alternative structure. The region surrounding a black hole therefore acts as a natural laboratory for testing gravitational theories. General relativity makes specific predictions regarding orbital motion, light-bending energy emission, and space-time geometry. Observations from telescopes and gravitational wave detectors repeatedly confirm these predictions with increasing precision. Despite the dramatic nature of these environments, they remain part of the observable universe. Light generated in accretion disks can escape and travel across space. Radiation from surrounding gas can be measured. Orbital motions can be tracked. The outer environment of a black hole remains accessible to observation and scientific investigation. Importantly, nothing about this surrounding region requires crossing an event horizon. Astronomers can learn a great deal while remaining entirely outside the boundary that defines the black hole itself. The disk, the jets, the orbiting stars, and the bending of light all belong to the exterior environment. They provide the evidence from which modern understanding of black holes is constructed. As one moves conceptually inward through this environment, gravity becomes increasingly dominant. The behavior of matter grows more extreme. Light follows more strongly curved paths. Orbital motions accelerate. The familiar conditions found elsewhere in galaxies gradually give way to a realm where space-time itself plays an increasingly visible role. The outer neighborhood of a black hole thus forms a transitional region between the ordinary cosmic structures of galaxies and the deeper gravitational domain that begins at the boundary known as the event horizon. At the center of the environment surrounding a black hole lies a boundary unlike any other known in nature. This boundary is called the event horizon. It marks the point at which the gravitational structure of spacetime changes in a fundamental way. Outside the event horizon, light and matter may still travel outward under appropriate conditions. At the event horizon and beyond, according to current understanding, every possible future path leads inward. The event horizon is often imagined as a physical surface. Everyday experience encourages such comparisons because most boundaries encountered in ordinary life separate one region from another through tangible material. The surface of a planet divides atmosphere from ground. The surface of water separates air from liquid. The event horizon is different. It is not made of matter. No solid shell surrounds the black hole. Instead, the event horizon is a geometric boundary defined by the structure of space-time itself. General relativity predicts the existence of this boundary when sufficient mass becomes concentrated into a sufficiently compact region. The resulting curvature of space-time becomes so extreme that escape ceases to be possible. Even light, which normally travels at the greatest speed allowed by nature, cannot move outward once it crosses the horizon. This inability to escape gives black holes their defining characteristic. From far away, the event horizon appears deceptively simple. It forms a roughly spherical boundary around a non-rotating black hole. Rotating black holes possess somewhat more complex geometries, but the essential concept remains the same. The horizon represents the outer limit beyond which signals cannot return to distant observers. An important feature of the event horizon is that nothing special necessarily exists there as a physical barrier. According to general relativity, an observer falling freely toward a sufficiently large black hole may not encounter any material surface upon reaching the horizon. Local conditions at the crossing point can remain relatively ordinary. The significance of the horizon emerges from its global role within spacetime rather than from any locally detectable wall. This aspect often appears counterintuitive. Human intuition develops within environments governed by weak gravity and familiar physical boundaries. The event horizon belongs to a realm where space-time geometry itself determines what can and cannot occur. Its importance arises not because something blocks motion outward, but because outward paths no longer lead away from the black hole. For distant observers, the behavior of objects approaching the horizon appears unusual. Light emitted from material moving closer to the horizon becomes increasingly stretched toward longer wavelengths. This effect, known as gravitational redshift, occurs because gravity influences the behavior of light and time. As a result, signals arriving from near the horizon lose energy and become progressively more difficult to detect. Time itself also appears affected. Clocks located closer to a strong gravitational field run differently relative to clocks farther away. To a distant observer, processes occurring near the event horizon seem to proceed more slowly. Material approaching the horizon appears increasingly delayed. The signals it sends require more time to arrive and become weaker through gravitational redshift. These effects do not imply that local time actually stops for the falling object. From the perspective of the object itself, events continue normally. The apparent slowing arises from the relationship between different observers situated in different gravitational environments. General relativity describes these differing perspectives consistently within its mathematical framework. The event horizon therefore separates two distinct observational realities. Outside observers receive increasingly limited information from material approaching the horizon. Meanwhile, an object moving inward continues along its own path without encountering an obvious physical boundary. The contrast reflects the unusual nature of spacetime near black holes. Modern observations provide indirect evidence supporting the existence of event horizons. Astronomers observe compact objects whose behavior matches black hole predictions remarkably well. The absence of visible surfaces in many systems also supports the horizon concept. Material falling toward these objects behaves differently than it would if a solid surface existed. While direct observation of the horizon itself remains impossible in the ordinary sense, the accumulated evidence strongly favors its existence. Images obtained by global networks of radio telescopes further reinforce this conclusion. The dark central regions observed around certain supermassive black holes correspond closely to theoretical expectations associated with event horizons. The surrounding bright material and distorted light patterns align with calculations based on general relativity. The event horizon also occupies a central position in modern theoretical physics. Questions concerning information quantum effects and the nature of spacetime frequently focus on this boundary. Scientists continue investigating how gravity and quantum theory interact in such extreme environments. While many aspects remain subjects of active research, the horizon itself remains a well-established prediction, supported by substantial observational evidence. Importantly, the event horizon does not act as a destructive force in its own right. It does not tear matter apart simply because it is crossed. The gravitational conditions experienced at the horizon depend on the size of the black hole. For very large black holes, the local gravitational gradient at the horizon may be relatively modest. More extreme effects often occur deeper within the gravitational field rather than at the boundary itself. As a conceptual destination, the event horizon represents the limit of direct communication with the external universe. Beyond it, no signal can return. Every outward route closes. Every future path leads further inward. For observers, remaining outside the horizon marks the edge of accessible information. It is the boundary that transforms an extremely massive object into a black hole. Within the layered structure of a black hole, the event horizon serves as the threshold between the observable exterior environment and the hidden interior. Everything discussed so far, the galaxies, the cosmic web, the expanding universe, the accretion disks, the orbiting stars, and the bending of light belongs to regions from which information can still emerge. The event horizon stands as the final boundary of that accessible realm, defining the entrance to a domain where current observation can no longer directly follow. Near the event horizon, space and time behave in ways that differ profoundly from ordinary experience. These differences do not arise because the laws of physics cease to operate. Rather, they emerge because gravity becomes so strong that the geometry of space-time itself becomes impossible to ignore. In everyday life, such effects are extremely small. Around planets, stars, and even most regions of galaxies, they remain subtle. Near a black hole, however, they become central features of reality. The concept of space-time provides the foundation for understanding these effects. General relativity describes space and time as aspects of a single interconnected structure. Massive objects influence this structure through their presence. Matter and energy shape space-time, and space-time guides the motion of matter and energy. Near a black hole, this relationship becomes especially apparent. Far from a black hole, space-time appears relatively flat. Objects move along predictable paths. Clocks situated in different locations remain closely synchronized if other influences are absent. Light travels in nearly straight lines across large regions. The familiar behavior of everyday experience emerges naturally in such environments. As one approaches a black hole, gravity grows stronger. The curvature of space-time increases. Paths followed by matter and light become increasingly affected by the geometry surrounding the black hole. Objects that would otherwise travel along simple trajectories begin following more dramatically curved routes. One of the most important consequences involves the passage of time. General relativity predicts that gravity influences the rate at which time passes. This phenomenon is called gravitational time dilation. A clock located in a stronger gravitational field runs more slowly relative to a clock located farther away in a weaker field. This effect is not merely theoretical. Experiments conducted on Earth confirm it with remarkable precision. Clocks positioned at different elevations measure slightly different rates of time because Earth's gravity varies with distance from the planet's center. The effect remains small in everyday circumstances but becomes measurable using modern instruments. Near a black hole, gravitational time dilation becomes far more pronounced. A clock approaching the event horizon ticks more slowly, relative to a clock located far from the black hole. To a distant observer, processes occurring near the horizon appear increasingly delayed. Signals arriving from that region become stretched and weakened as they travel outward through the intense gravitational field. From the perspective of the observer near the black hole, however, local time continues normally. Heartbeats, atomic processes, and physical events proceed according to the local clock. Nothing within the immediate surroundings indicates that time itself has stopped. The difference arises when comparing measurements made by observers situated in different gravitational environments. This distinction is central to understanding black hole physics. General relativity does not assign a single universal clock governing all events everywhere. Instead, the passage of time depends partly on location and motion. Near a black hole, these differences become large enough to influence observations dramatically. Space itself also behaves differently. Distances near a black hole do not correspond exactly to ordinary geometric expectations. The curvature of space-time alters the relationships between locations. Light rays bend. Orbital paths change. The geometry becomes increasingly unlike the nearly flat space familiar from daily life. One visible consequence is gravitational lensing. Light passing through curved space-time follows bent trajectories. Near a black hole, the bending can become extreme. Some light rays may circle the black hole before escaping. Others may become trapped entirely. This behavior contributes to the unusual appearance predicted for the regions surrounding event horizons. Astronomers studying images of black hole environments observe features consistent with these predictions. Bright material orbiting near the black hole appears distorted because the light reaching telescopes has followed curved paths through strongly warped space-time. The resulting patterns provide important tests of general relativity under extreme conditions. Orbital motion also changes significantly. Around planets and ordinary stars, stable orbits exist across a wide range of distances. Near a black hole, stable orbits become increasingly restricted. There exists an innermost region beyond which stable circular motion is no longer possible. Material entering this zone tends to spiral inward rather than continuing indefinitely in a stable orbit. These effects influence accretion disks profoundly. Gas orbiting near the black hole moves at tremendous speeds. Friction, compression, and gravitational forces generate intense heat. The resulting radiation carries information about conditions within this strongly curved region of space-time. By analyzing such emissions, astronomers learn about environments that cannot be reproduced in laboratories. Rotation introduces additional complexity. Many black holes appear to rotate. General relativity predicts that rotating mass can influence surrounding spacetime through a phenomenon often called frame dragging. In simple terms, the rotation affects nearby spacetime itself. Objects and light moving close to a rotating black hole experience consequences of this altered geometry. Observations increasingly support the existence of rotating black holes. Measurements of accretion disks, jets, and gravitational waves suggest that rotation is common among astrophysical black holes. These findings align with theoretical expectations because the stars and gas from which black holes form generally possess angular momentum before collapse. Despite the unusual nature of these effects, the underlying physics remains consistent. General relativity continues to provide accurate predictions across a wide range of observations. The theory successfully describes gravitational time dilation, light-bending orbital behavior, and many other phenomena associated with black holes. Near the event horizon, therefore, reality is not governed by different laws but by familiar laws operating under extraordinary conditions. Space and time reveal properties that remain hidden in weaker gravitational fields. Clocks diverge, light curves, distances behave differently. Motion follows paths shaped by intensely warped space-time. This region represents one of the clearest demonstrations that gravity is not merely a force acting through space, but an expression of space-time geometry itself, visible in its most dramatic observable form near the threshold of a black hole. Beyond the event horizon lies a region that no observation can directly examine. Light emitted from within cannot return to distant observers. Signals cannot escape. Telescopes, regardless of their sophistication, cannot peer into this hidden interior. As a result, scientific understanding of the inside of a black hole relies not on direct observation, but on theoretical models built from the laws of physics that successfully describe the regions outside. General relativity provides the primary framework for exploring this concealed domain. The equations of the theory can be extended beyond the event horizon, producing mathematical descriptions of what should occur within. These descriptions reveal an interior very different from ordinary space. The familiar concepts of direction, distance, and future behavior begin to take on unusual meanings. Outside, a black hole movement remains flexible. An object can travel in many directions. It can move toward the black hole or away from it. Different futures remain possible. Beyond the event horizon, the situation changes fundamentally. According to the simpler solutions of general relativity, all future-directed paths lead deeper inward. Moving toward the center becomes as unavoidable as moving forward in time. This comparison requires careful interpretation. it does not mean that inward motion literally becomes time. Rather, the geometry of space-time inside the horizon becomes arranged in such a way that progression towards smaller radial distances cannot be avoided. Just as an ordinary observer cannot choose to stop moving into the future, an object inside the horizon cannot choose a path that permanently increases its distance from the center. Theoretical descriptions suggest that the interior remains a dynamic region. Matter crossing the horizon continues inward. Any gas-dust radiation or stars that enter the black hole contribute to the evolving conditions inside. The black hole is therefore not an empty cavity enclosed by the event horizon. Instead, it is a region where space-time geometry directs all motion toward increasingly compressed states. For non-rotating black holes, the mathematical picture appears relatively simple. The interior funnels all trajectories toward a central destination predicted by general relativity. This prediction emerges consistently from the equations and represents one of the defining features of classical black hole models. Rotating black holes produce more complicated theoretical structures. Most real astrophysical black holes are expected to rotate because the stars and gas from which they form possess angular momentum. Rotation modifies the geometry of spacetime. The resulting mathematical solutions contain additional features not present in the simplest non-rotating case. Some theoretical descriptions of rotating black holes include multiple horizons and complex interior regions. These structures arise naturally within certain mathematical solutions of general relativity. However, determining whether such idealized features persist in realistic black holes remains challenging. Small disturbances in falling matter and quantum effects may significantly alter the interior structure. Consequently, some predictions remain uncertain. The difficulty arises because the interior cannot be directly tested through observation. Science generally advances by comparing theoretical predictions with measurements. Inside a black hole, this process becomes severely limited. The event horizon prevents information from returning. As a result, confidence decreases as theoretical exploration proceeds deeper into regions inaccessible to observation. Nevertheless, some conclusions remain robust. General relativity consistently predicts that conditions inside a black hole become increasingly extreme. Density rises, curvature of spacetime grows stronger, gravitational effects intensify. The exact details may depend on factors such as rotation and the properties of infalling matter, but the overall trend appears unavoidable within classical theory. Another important aspect concerns the passage of time experienced by an object that crosses the horizon. Contrary to some popular portrayals, classical general relativity does not predict that an observer remains suspended indefinitely at the horizon. From the observer's own perspective, motion continues. The journey inward proceeds. The event horizon itself is crossed within a finite amount of proper time, meaning time measured along the observer's own path. The distinction between external and internal perspectives becomes especially important here. To distant observers, signals from near the horizon appear increasingly delayed and redshifted. To the infalling observer, events continue according to local clocks. General relativity accommodates both descriptions without contradiction because they refer to different frames of reference. The interior also raises questions regarding information. Matter carrying information about its previous state can fall into a black hole. What ultimately happens to that information remains one of the major topics in theoretical physics. Research involving quantum theory, black hole thermodynamics, and related fields seeks to understand how information behaves in these extreme environments. While important progress has been made, no complete consensus has yet emerged regarding every aspect of the problem. Theoretical studies further suggest that black holes are not entirely isolated from quantum effects. Calculations developed during the 20th century indicate that black holes may slowly emit radiation through quantum processes occurring near the event horizon. This prediction, commonly known as Hawking radiation, implies that black holes may gradually lose mass over extraordinarily long timescales. For astrophysical black holes, however, the effect remains far too weak to observe directly with current technology. Inside the horizon itself, classical general relativity remains the principal guide. The theory describes a space-time geometry directing all future paths inward. Matter continues moving toward regions of increasing gravitational intensity. The familiar freedom to choose outward trajectories disappears. Space and time become arranged in ways that differ fundamentally from ordinary experience. Yet even these sophisticated models carry limits. General relativity performs exceptionally well in many situations, but physicists recognize that it may not provide a complete description under the most extreme conditions. The deeper interior of a black hole likely involves regimes where quantum effects become important. Since a fully successful theory combining gravity and quantum physics has not yet been established, uncertainties remain. Thus, the interior revealed by current models is both impressive and incomplete. General relativity provides a coherent mathematical picture extending beyond the event horizon and describing the inward evolution of space-time. At the same time, the deepest regions approach conditions where present theories may no longer be sufficient. The hidden interior therefore stands as a domain understood through powerful theoretical insight, yet still marked by important unanswered questions at its most extreme depths. As theoretical exploration continues deeper into the interior of a black hole, the predictions of general relativity approach a region where the theory itself signals profound limitation. This region is associated with what physicists call a singularity. The singularity occupies a unique place in modern science because it does not merely represent an unusual object or an extreme environment. Instead, it marks a point where current mathematical descriptions cease to provide a complete account of physical reality. In the simplest black hole solutions derived from general relativity, every path inside the event horizon eventually leads toward a central singularity. As matter moves inward, density increases. The curvature of space-time grows stronger. The equations indicate that these quantities continue increasing until they reach values that become effectively infinite. At this stage, the mathematical description breaks down. The appearance of infinities in physics is often interpreted as a warning sign. It does not necessarily mean that nature literally contains infinite density or infinite curvature. Rather, it suggests that the theory being used has reached the limits of its applicability. Similar situations have occurred before in the history of science. Older theories sometimes predict impossible or undefined results when applied beyond the conditions for which they are valid. New theoretical frameworks later provide more complete descriptions. For this reason, physicists generally do not regard singularities as fully understood physical objects. Instead, they are viewed as indications that present theories are incomplete under certain extreme circumstances. General relativity remains extraordinarily successful across a vast range of observations from planetary motion to gravitational waves. Yet the theory was not designed to incorporate quantum physics, which governs behavior at very small scales. The conflict emerges because black hole interiors eventually involve both immense gravitational effects and extremely compressed states of matter. Gravity is described by general relativity. Quantum phenomena are described by quantum theory. Both frameworks work remarkably well in their respective domains. However, combining them into a single unified theory remains one of the major challenges in modern physics. As matter approaches the conditions associated with a classical singularity, quantum effects are expected to become increasingly important. The exact nature of those effects remains uncertain because a complete theory of quantum gravity has not yet been established. Several approaches are actively investigated, but no single solution has achieved universal acceptance. Observations provide little direct guidance in this region because the event horizon prevents information from escaping. Scientists therefore rely heavily on theoretical reasoning, mathematical consistency, compatibility with established observations and connections to broader physical principles all contribute to evaluating proposed ideas. One possibility is that quantum processes prevent true singularities from forming. In such models, matter may reach extremely high densities without becoming infinitely compressed. The details vary among different theoretical approaches. Some suggest that spacetime itself acquires a fundamentally different structure at very small scales. Others propose new forms of quantum behavior that alter gravitational collapse. At present, however, observations do not allow scientists to determine which possibility, if any, accurately describes nature. The evidence strongly supports the existence of black holes and event horizons. It also supports the success of general relativity in regions outside the deepest interior. Beyond that point, certainty becomes more limited. The singularity therefore occupies a special position in black hole research. It is not simply another location within spacetime that can be mapped and described with confidence. Rather, it marks the boundary between established theoretical prediction and the unknown. The equations guide understanding toward this region, but they also indicate where their own reliability becomes questionable. Rotating black holes introduce additional complexity. Certain mathematical solutions contain structures more intricate than the single, central singularity predicted for non-rotating cases. These solutions may include ring-shaped singularities and other unusual features. Some interpretations of the mathematics suggest possibilities that appear highly exotic. However, many physicists remain cautious regarding such predictions, because idealized solutions may not fully represent realistic astrophysical black holes. Small disturbances in falling matter and quantum effects could substantially modify these theoretical structures. Since direct observation is impossible, distinguishing between mathematical possibilities and physical realities becomes particularly difficult. As a result, many detailed interior predictions remain subjects of ongoing investigation rather than established conclusions. The study of singularities extends beyond black holes alone. Similar questions arise when cosmologists examine the earliest moments of cosmic history. Models describing the expansion of the universe can also be traced backward towards states of extraordinary density and temperature. There too, singularities often appear in classical calculations. This parallel suggests that the limitations encountered in black hole interiors may connect to broader questions about the origin and structure of spacetime itself. The search for a deeper theory therefore carries significance beyond understanding black holes. It may reveal new principles governing gravity-matter energy and the universe as a whole. Black holes provide one of the most extreme natural environments in which these questions emerge, making them valuable laboratories for theoretical investigation even when direct observation remains impossible. Despite the uncertainty surrounding singularities, several conclusions remain secure. Black holes are real astronomical objects. Event horizons are strongly supported by evidence. General relativity accurately describes many aspects of black hole behavior. The difficulties arise only when theoretical exploration reaches conditions where gravity becomes extraordinarily intense and known physics approaches its limits. The singularity thus serves as a signpost indicating the frontier of current knowledge. It shows where successful theories cease to provide complete answers. Rather than representing a final understanding, it reveals an area where deeper explanations are needed. In this sense, the singularity is less a destination than a boundary marking the transition from well-tested physics into a realm that remains only partially understood. Within the layered journey inward through black holes, this is the deepest point reached by established classical theory. Beyond it lies territory where certainty fades, and fundamental questions concerning space-time gravity and quantum reality remain open. This singularity stands at that threshold, highlighting both the power of modern physics and the limits that science continues to explore. At the limits of classical black hole theory, where singularities appear and established descriptions become incomplete, some physicists begin exploring whether black holes might connect to larger cosmological processes. These ideas do not arise from direct observation. Rather, they emerge from attempts to understand what could occur when gravitational collapse reaches conditions beyond the reach of current theories. Among the possibilities considered is the notion that black holes may somehow give rise to new expanding regions of space-time. This concept occupies a different category from the well-established properties of black holes already supported by observation. Event horizons, accretion disks, gravitational waves, and stellar motions all rest upon extensive evidence. The proposal that black holes might be connected to the birth of new universes remains speculative. It is studied because certain mathematical and theoretical considerations make it worth examining, not because observations have confirmed it. The motivation begins with a simple question. If singularities indicate the breakdown of known physics rather than a literal end of space-time, what replaces them? A future theory combining gravity and quantum physics may eliminate the singularity entirely. If that occurs, gravitational collapse might continue through processes not yet understood. Some theoretical models suggest that instead of terminating in a singular state, space-time could evolve into a new expanding region. In these scenarios, the interior of a black hole does not end at an infinitely compressed point. Instead, extreme compression is followed by a transition into another phase of space-time. The resulting region may expand in ways resembling the early evolution of a universe. From the perspective of observers within that expanding region, the environment could appear similar to a cosmos, emerging from a hot, dense beginning. Such ideas are often explored through mathematical models that modify classical gravity at very high densities. Different approaches produce different outcomes. Some models replace singularities with quantum states that prevent infinite compression. Others propose geometric transitions within space-time itself. Although the details vary, many share a common theme: the deepest interior of a black hole may be more complex than classical theory alone predicts. An important aspect of these proposals is that the new region, if it exists, would generally remain disconnected from the original external universe. The event horizon prevents ordinary communication outward. Any expanding space-time emerging beyond the deepest interior would not provide an easy pathway back to the parent cosmos. Consequently, direct observational tests become extremely difficult. This challenge places such ideas in a unique scientific position. They are not arbitrary fantasies. They often arise from serious attempts to address unresolved theoretical problems. Yet they also lack direct empirical confirmation. As a result, they remain hypotheses rather than accepted descriptions of reality. Some researchers have explored whether black holes could participate in a kind of cosmic reproduction. In these speculative frameworks, each black hole might generate a new expanding universe with slightly different physical characteristics. Over immense spans of cosmic history, universes producing many black holes could become more common. Such ideas attempt to explain certain observed features of nature through a process analogous in a very loose sense to selection. These proposals remain controversial and unproven. They are valuable primarily because they encourage new ways of thinking about the relationship between gravity cosmology and fundamental physics. Whether nature actually operates in this manner remains unknown. The possibility of new universes emerging from black holes also influences discussions regarding cosmic origins. Modern cosmology describes an early hot and dense phase of the observable universe. The Standard Model successfully explains many observations, including the cosmic microwave background and the large-scale distribution of galaxies. However, questions concerning the ultimate origin of that early state remain open. Some theoretical researchers therefore examine whether black hole-based scenarios could contribute to a deeper explanation. In these investigations, the focus often shifts from individual astronomical objects to the structure of spacetime itself. A black hole becomes more than a collapsed star or a galactic centerpiece. It becomes a potential bridge between different regions of reality, at least within certain mathematical frameworks. The idea is striking, but it must be approached with caution, because the supporting evidence remains indirect. Current observations neither confirm nor decisively exclude many of these possibilities. The event horizon prevents direct access to the relevant regions. Researchers must therefore rely on consistency with known physics, mathematical coherence, and compatibility with established observations of the universe. Theoretical work in this area frequently intersects with efforts to develop quantum gravity. Since classical singularities signal the breakdown of general relativity, any successful replacement theory must address what occurs under such conditions. Whether the answer involves new universes, modified spacetime structures, or something entirely different remains uncertain. Importantly, the existence of these hypotheses does not imply that ordinary black holes are mysterious portals in the popular sense. Observed black holes behave according to well-understood gravitational principles. Their effects on surrounding stars, gas and radiation align closely with established theory. The speculative ideas concern regions beyond the reach of current observation, not the behavior of black holes in their observable environments. Nevertheless, the possibility that gravitational collapse could connect to cosmic creation remains one of the most intriguing concepts explored in theoretical physics. It arises naturally from attempts to move beyond singularities and understand what deeper laws might govern space-time under extreme conditions. Within the inward journey through the layers of black hole understanding, this stage marks a transition from established interior models toward broader cosmological possibilities. The black hole ceases to be viewed solely as an endpoint of collapse, and becomes in some theoretical frameworks a participant in larger processes shaping the structure of reality itself. Whether these ideas correspond to nature remains unknown, but they form an important part of the scientific exploration of what may lie beyond the limits of current theory. The idea that an entire universe might exist within a black hole represents one of the most ambitious hypotheses ever considered in theoretical cosmology. It extends beyond the proposal that black holes could generate new expanding regions of space-time. Instead, it suggests a possibility directly related to the observable universe itself. According to certain models, the cosmos inhabited by galaxies, stars, planets, and observers could exist within the interior of a larger black hole-like structure embedded in apparent reality. This concept emerges from attempts to connect black hole physics with cosmology. The starting point is a curious similarity. The observable universe appears to have begun in a hot, dense state and has expanded over billions of years. Black holes, meanwhile, involve regions where matter becomes highly compressed under gravity. Both situations bring physics toward conditions where current theories encounter profound challenges. Some researchers have therefore explored whether these two domains might be related. If singularities do not represent literal physical infinities, perhaps the interior of a collapsing region could evolve into an expanding spacetime. In that case, what appears from one perspective as a black hole might appear from another perspective as a universe undergoing expansion. Within such models, observers living inside the expanding region would not perceive themselves as residing inside a black hole. Their observations would reveal galaxies' cosmic expansion, background radiation, and the familiar large-scale structures studied by astronomy. The surrounding parent reality would remain inaccessible because the geometry of space-time would prevent ordinary communication across the boundary separating the two regions. This feature is important. If the observable universe were connected to a larger external realm through black hole-like geometry, inhabitants of the interior would not necessarily have direct observational access to that exterior. Their measurements would be confined to the space-time available within their own cosmos. Several variations of the black hole universe idea have been proposed. Some arise from modifications of general relativity. Others emerge from approaches to quantum gravity. Still others explore mathematical similarities between cosmological solutions and black hole geometries. Although these models differ substantially in detail, they share a common theme: the possibility that cosmic expansion and gravitational collapse may represent different aspects of a deeper space-time process. The attraction of the hypothesis lies partly in its attempt to address questions concerning cosmic origins. The standard cosmological model successfully describes the evolution of the observable universe from an early hot and dense phase onward. It explains many observations with impressive accuracy, yet the ultimate origin of that initial state remains uncertain. Black hole universe models seek to place the beginning of cosmic expansion within a broader physical context. In some formulations, the birth of a universe corresponds to the collapse of matter in a parent cosmos. The interior expansion then unfolds according to physical laws operating within the newly formed space-time region. From the viewpoint of inhabitants inside the beginning may resemble a cosmological origin. From the viewpoint of the parent universe, a black hole may have formed. Such ideas remain highly speculative. No observation currently demonstrates that the observable universe exists within a black hole. The models are investigated because they offer mathematically interesting possibilities, and because they connect several unresolved questions in cosmology and gravitational physics. An important challenge concerns reproducing the detailed properties of the observed universe. Any successful model must account for cosmic expansion, the cosmic microwave background, the distribution of galaxies, the abundance of chemical elements, and many other measurements. The standard cosmological model already explains these observations effectively. Therefore, alternative proposals must match that success, while also providing additional explanatory value. Researchers have examined whether certain observed features could be consistent with a black hole origin scenario. Some studies investigate the geometry of space-time. Others explore rotational effects, cosmic structure formation, or modifications to early universe evolution. Results vary depending on the specific model under consideration. At present, no version has achieved the level of empirical support enjoyed by the standard cosmological framework. Another difficulty involves testability. Scientific theories gain strength through observations capable of confirming or challenging their predictions. If the observable universe is entirely enclosed within a black hole-like region, direct access to the exterior may be impossible. This limitation complicates efforts to distinguish such models from other explanations. Nevertheless, the idea continues to attract interest because it encourages physicists to think about black holes and cosmology as potentially connected phenomena rather than completely separate subjects. Both involve extreme conditions. Both raise questions concerning space-time gravity and origins. Both reveal areas where current theories may be incomplete. Within these models, the phrase living inside a black hole does not imply existence within a dark cavity surrounded by visible walls. The concept is far more abstract. It refers to the possibility that the geometry governing the observable universe may correspond from a higher level perspective to the interior structure associated with a black hole in another space-time. The everyday experience of stars, galaxies, and cosmic expansion would remain unchanged. From the standpoint of present evidence, the observable universe is accurately described by established cosmological theories involving expansion from an early hot and dense state. The black hole universe hypothesis does not replace that framework. Rather, it attempts to embed it within a larger theoretical picture. Whether nature actually follows such a picture remains unknown. As scientific understanding advances, future developments in quantum gravity cosmology and black hole physics may clarify these possibilities. For now, the concept remains a carefully considered but unconfirmed idea. It occupies a region of inquiry where mathematics, cosmological observation, and theoretical imagination meet. Within the progression from the outer universe toward the deepest layers of black hole thought, this stage represents the central question itself. The black hole is no longer viewed merely as an object within the cosmos. Instead, the cosmos becomes the object under examination. The possibility being explored is whether the entire observable universe may itself be part of a larger gravitational structure, hidden within the interior of a reality that remains beyond present observation. Once the possibility has been considered that the observable universe could exist within a black hole-like structure, the next step is not to assume the idea is correct. Science proceeds by comparing hypotheses with evidence. Any proposal concerning the nature of the universe must be evaluated against observations gathered from telescopes, satellites, particle detectors, gravitational wave observatories, and many other instruments. The strength of a scientific model depends not on how intriguing it appears, but on how successfully it explains reality. Modern cosmology rests upon a substantial body of observational evidence. One of its strongest foundations is the expansion of the universe. Measurements of distant galaxies consistently indicate that space itself expands on large scales. This conclusion is supported by galaxy redshifts observations of supernovae studies of large-scale structure and measurements of the cosmic microwave background. Together, these observations form a coherent picture of cosmic evolution extending across billions of years. The cosmic microwave background provides particularly important evidence. This faint radiation fills the sky in every direction and represents a remnant from an early stage of cosmic history. Its temperature varies only slightly from place to place, yet those tiny variations contain enormous amounts of information. Detailed measurements reveal patterns that agree remarkably well with predictions made by the standard cosmological model. The distribution of galaxies supplies another major source of evidence. Large surveys map millions of galaxies across vast regions of space. Their arrangement follows patterns expected from the growth of structure under gravity in an expanding universe. Simulations based on established cosmological principles reproduce many of the observed features with considerable accuracy. The abundances of light chemical elements also provide crucial tests. Hydrogen, helium, and small amounts of certain other elements form under conditions present during the early evolution of the universe. The observed proportions closely match theoretical calculations derived from standard cosmological models. This agreement represents one of the strongest successes of modern cosmology. Because the standard framework explains so many observations, any alternative proposal faces a demanding challenge. It must reproduce all these successful predictions while also offering a compelling reason to adopt a more complex interpretation. This requirement applies directly to black hole universe models. Some versions of the black hole universe hypothesis attempt precisely this. They do not reject cosmic expansion, the cosmic microwave background, or the formation of galaxies. Instead, they seek to explain these phenomena as processes occurring inside a universe that originated through gravitational collapse elsewhere. The goal is not necessarily to replace standard cosmology, but to extend it. The difficulty lies in finding distinctive predictions that can be tested. Many black hole universe models can be adjusted to resemble ordinary cosmology so closely that observational differences become difficult to identify. If two theories make identical predictions for all accessible observations, distinguishing between them becomes impossible through current empirical methods. Researchers therefore search for subtle signatures that might reveal differences. Some studies investigate whether rotational properties inherited from a parent black hole could leave detectable traces in cosmic structure. Others examine whether modifications to space-time geometry might influence the earlier stages of expansion. To date, no observation has provided decisive evidence supporting the hypothesis. At the same time, no observation directly proves that the idea is impossible. This distinction is important. Scientific uncertainty does not imply equal support for all possibilities. The standard cosmological model enjoys extensive empirical backing. Black hole universe scenarios remain speculative because they currently lack comparable observational confirmation. Yet they are not excluded simply because definitive evidence has not yet been found. The challenge of testing such ideas illustrates a broader issue in cosmology. The observable universe provides only one example of a cosmos available for study. Scientists cannot perform controlled experiments involving entire universes. Instead, they must infer underlying principles from observations of the single universe that can be examined. This limitation makes cosmology both powerful and inherently challenging. Black hole universe models also encounter theoretical questions. Any successful framework must remain consistent with general relativity, where that theory has been tested. It must also account for quantum effects under extreme conditions. Since a complete theory of quantum gravity remains unavailable, uncertainties persist regarding the deepest foundations of these proposals. Nevertheless, the investigation itself contributes valuable insights. By exploring black hole universe ideas, researchers probe the limits of current theories. They identify assumptions that might otherwise remain unnoticed. They examine connections between gravitational collapse, cosmic expansion, space-time geometry, and quantum physics. Even if a particular model ultimately proves incorrect, the process often advances understanding in other areas. Scientific history contains many examples where studying speculative possibilities leads to important discoveries. Not every hypothesis survives, but the effort to test and refine ideas frequently reveals new principles and observations. Black hole universe models occupy this tradition. They challenge existing assumptions while remaining subject to empirical scrutiny. The current balance of evidence favors the standard picture of an expanding universe described by modern cosmology. Observations of the cosmic microwave background galaxy distributions, chemical abundances, and gravitational phenomena all fit within that framework remarkably well. Black hole universe proposals remain intriguing alternatives that attempt to place this successful model within a larger context. From the perspective of scientific methodology, the distinction is clear. Established observations support cosmic expansion and the evolution of the observable universe from an early hot and dense state. Whether that state itself emerged from processes associated with a black hole in a larger reality remains unknown. The available evidence neither confirms nor demonstrates such a connection. This region of inquiry therefore represents a careful weighing of possibilities. It is the point where imaginative theoretical ideas encounter the discipline of observation. The question is no longer whether a black hole universe model can be conceived. It is whether nature provides evidence that such a model is true. At present, the answer remains uncertain, leaving the hypothesis as an interesting possibility still awaiting stronger empirical support. After moving from the observable universe through cosmic expansion, large-scale structure, black holes, event horizons, interior model singularities, and the possibility of universes emerging from gravitational collapse, the deepest perspective is not found in a final answer. Instead, it appears in the relationship between what is known and what remains uncertain. The question of whether the observable universe could exist within a black hole ultimately reveals something broader about the nature of scientific understanding itself. The history of astronomy demonstrates a gradual expansion of perspective. For much of human history, Earth appears to occupy a central position in the cosmos. Later observations show that Earth orbits the Sun. Further discoveries reveal that the Sun is one star among many within the Milky Way. The Milky Way itself becomes one galaxy among hundreds of billions. Each stage widens the known scale of reality. Black holes introduce another shift in perspective. They show that gravity can create regions where ordinary intuitions concerning space and time no longer provide reliable guidance. Event horizons demonstrate that information can become permanently inaccessible to distant observers. Singularities reveal places where successful theories encounter their limits. These discoveries do not simply add new objects to astronomical catalogues. They alter the framework through which reality is understood. The possibility that universes and black holes might be connected extends this pattern. It asks whether structures that appear separate at first glance may actually belong to a larger system. Although the idea remains unconfirmed, it reflects a recurring theme in science boundaries that once seemed fundamental, sometimes become parts of broader explanations. At the same time, modern cosmology provides a reminder that evidence remains the foundation of scientific knowledge. The observable universe is not merely a philosophical concept, it is a physical domain studied through measurements. Telescopes observe distant galaxies. Satellites map background radiation. Detectors measure gravitational waves. Scientific understanding advances because observations continuously test theoretical ideas. This relationship between theory and observation becomes especially important when addressing questions concerning cosmic origins. Human beings naturally seek explanations for beginnings. Why the universe possesses its particular properties, why cosmic expansion occurs, why physical laws take their observed forms. Yet nature does not guarantee that every question will yield an immediate answer. Some problems require decades or centuries of investigation. The black hole universe hypothesis occupies precisely such a frontier. It is not established knowledge, neither is it mere fantasy. It exists within a category of ideas motivated by genuine theoretical challenges and explored through serious scientific work. Researchers investigate it because known physics encounters unresolved questions regarding singularities, quantum gravity, and the earliest stages of cosmic history. One lesson emerging from these investigations is humility regarding the limits of present understanding. General relativity succeeds across an extraordinary range of conditions. Quantum theory explains phenomena with remarkable accuracy, yet the two frameworks remain incompletely unified. Black holes expose this gap with unusual clarity. Their deepest interiors appear to require insights extending beyond current theories. Another lesson concerns the scale of reality. Human experience unfolds within a narrow range of environments. Daily life takes place on the surface of a planet orbiting an ordinary star. The universe revealed by astronomy extends far beyond those familiar conditions. Galaxies span enormous distances. Black holes curve space-time dramatically. Cosmic history stretches across billions of years. Scientific investigation repeatedly shows that reality is often larger and more intricate than intuition suggests. Despite this complexity, a surprising degree of order emerges. The same physical laws appear throughout the observable cosmos. Light from distant galaxies follows recognizable patterns. Gravity operates consistently across scales. Mathematical descriptions developed on Earth successfully explain phenomena occurring billions of light-years away. This coherence provides one of the strongest reasons for confidence in scientific inquiry. Whether the observable universe exists within a larger black hole-like structure remains unknown. Future observations may reveal evidence supporting such ideas. They may instead favor entirely different explanations. New theories may emerge that transform understanding in unexpected ways. At present, the available evidence supports an expanding universe, evolving according to principles described by modern cosmology, while deeper questions regarding ultimate origins remain open. The significance of the black hole universe concept therefore lies partly in what it encourages scientists to investigate. It connects cosmology with gravitational physics. It highlights the need for a successful theory of quantum gravity. It motivates the search for observational signatures capable of distinguishing among competing explanations. Even without confirmation, the hypothesis contributes to the broader effort to understand reality. Viewed from the widest perspective, the journey through black hole theory returns attention to the observable universe itself. Galaxies continue moving through expanding space. Stars continue forming and evolving. Black holes continue influencing their surroundings. The cosmos remains accessible through observation measurement and careful reasoning. Scientific progress occurs not through certainty alone, but through the continual refinement of understanding. The question of living inside a black hole remains unanswered. Current observations neither establish nor eliminate the possibility. Yet the investigation illuminates something enduring about science. Knowledge grows by exploring the edge between the known and the unknown. Every answer reveals new questions. Every boundary invites closer examination. Black holes, perhaps more than any other known objects, occupy that boundary. In this sense, the deepest level of black hole exploration is not the singularity, the event horizon, or even the hypothesis of nested universes. It is the recognition that the universe still contains mysteries worthy of patient study. The observable cosmos provides evidence. Theory provides interpretation. Between them lies an ongoing search for understanding that continues to expand much like the universe itself. As the exploration settles into stillness, the observable universe remains spread across unimaginable distances, filled with galaxies drifting through expanding space. Countless stars shine within those galaxies. Planets circle their suns. Black holes rest within stellar remnants and galactic centers carrying gravity to some of its most extreme expressions. Yet even these remarkable objects exist as part of a larger cosmic landscape that continues to reveal itself through observation. The journey inward through the layers of black hole understanding reaches a point where certainty gradually gives way to possibility. Established observations describe the expansion of the universe, the structure of galaxies, the presence of event horizons, and the influence of gravity on space and time. Beyond those well-tested regions lie questions that remain open. The deepest interiors of black holes, the nature of singularities, and the ultimate relationship between gravity and quantum physics continue to invite investigation. The idea that an entire universe could exist within a black hole remains one of those unanswered possibilities. It stands not as a conclusion, but as a reminder that scientific knowledge grows through careful exploration of uncertainty. Some ideas become established through evidence. Others remain provisional, waiting for future observations and deeper theories. Both play a role in the long process of understanding reality. Across billions of years of cosmic history, stars are born, evolve, and fade. Galaxies gather into clusters and filaments. Space continues to expand. Light travels immense distances, carrying information from distant epochs. Through that light, humanity gradually uncovers the structure of the cosmos and the laws that shape it. For now, the observable universe remains the home of all direct knowledge. Whether it exists alone or as part of a larger structure beyond present understanding remains unknown. The night sky offers no final answer, only a vast and quiet invitation to continue observing. The galaxies remain in motion. The black holes remain hidden behind their horizons. The universe continues its slow evolution through space and time, carrying its deepest mysteries forward into the future.